So let's summarize
Maybe a
what
bit
we
sad,
talked
yeah.
about yesterday. So we said we kind of talked about how we, three-dimensional creatures in a three-dimensional universe. How do we perceive the universe? What kind of sensory input do we get?
We have
Two
two
dimensions.
dimensions to put together.
Two dimensions. We have all kinds of tricks that we can use to process in our brains that two-dimensional information, and we can build a three-dimensional model, right? We understand the three dimensions well. I know from experience that if I walk over here, even though I can't see Lily right now, she's still back there, right? I mean, I can link historically the fact that I saw her here, I don't see her here. That two-dimensional data is all we need to reconstruct our three-dimensional world, right? So where we kind of left off is we wanted to see how that relates to the Flatlanders, right? So the Flatlanders living in a two-dimensional universe, we've got to try to before we can really understand how gravity works in our universe, we've got to try to visualize how it works in theirs, right? We have the benefit of an extra dimension here though, so we can actually see, we're gonna be able to see the warpings that impact their universe in a way that we can't in our own, right? So but we got to take just a second here and we got to build to the best we can. We're never going to be able to do this perfectly because we're not two-dimensional, but we have to at least have an appreciation for the limitations that they have, right? So what did we say yesterday about, what do we call her, Mrs. Scarlet? What she saw of Mr. Blue. First of all, what does she see of her universe?
Just a line.
Okay, it's a line, right? But now, hang on here, a line, that makes sense. If I stick my head into the plane of flatland, what am I going to see? I'm going to see presumably a white line all the way, that would make a complete 360-degree angle around me, right? As I turn, I'll just see this continuous white line. But to me, I see that because I also, as I turn this way, or to make things more convenient, I'm going to pick flatland up and I'm going to pull it down over my head, right? I would see a horizontal white line, but above and below that, I would see something else. I would see the white line embedded in a two-dimensional field of vision, right? Get that? Do they see that?
No.
They can't, right? They can't see that because they only live within their universe. Cosmologists, the string theorists surmise, and this is legitimate, this is a strong possibility, that if you adhere to multiverse theory, it's entirely possible that about 6 centimeters away from our universe, through what we might call hyperspace, if it really does work the way that they say it works, there could be another external universe that's right there, but we have no access to it. There's some recent data that suggests it has to do with that this travel outside of the membrane of our universe might have some impact on the way gravity works, but we could never get there, even if it is true. Yeah.
So because the universe is always expanding, does that mean you can actually hit something?
Well, not necessarily, because this gets complicated, but in multiverse theory it would say that the universe is actually expanding slower than the space in which it's embedded. It's called an inflaton field, and it would be like thinking like a pocket of air in a loaf of bread as the bread rises, right? The bubble's going to grow. How come the bubble grows? Because the matrix in which it sits is expanding. So it's a little more complicated than just saying the universe is expanding into something that's just empty, right? Yeah.
So could there then be like a multiverse?
Absolutely, yeah, and this is all pretty speculative, and it's very difficult, if not impossible, to try to find evidence from the inside that would corroborate some of this. This is what the string theorists tell us. It's possible that when we look at the fine articulation of as we launch satellites that can look at ever and ever finer solid angles, with more granular precision at the cosmic microwave background radiation, we might see there are some mathematical predictions about the kinds of patterns that we ought to see that would indicate that maybe there is some interaction going on. But that's still, at the minimum, probably 10 to 20 years away. But we'll talk, kind of when we have a break and we can really get into some weird stuff, we'll talk about the 4 classifications of possible multiverses, just because it's kind of fun. And it ties in with quantum mechanics a little bit too. And the mathematics is just daunting, but we don't have to obviously get into the mathematics. But for now, the point I just want to make here is, we said yesterday that if we drop the pen, I asked you the question, what's going on? You told me, what's gravity? What's gravity? It's a force. Well, what's that? That's where we kind of run into a snag. We can describe quantitatively with great accuracy. You guys can all do this. You could tell me how fast is it going when it's dropped that far, right? You could tell me. You could use your quantum or your kinematics equations and come up with a solid answer that would be very accurate. You can tell me a lot about the interaction of the gravitational force with objects in our room, right? We can describe it well, but we never really talked about the causality, and that's where we're going with this. We made the bold statement that when you drop the pen, it's actually slipping into a gravity well, but you can't see the well, right? These guys are going to experience, as we're going to see, are going to experience the same thing, but we'll have the benefit of being able to actually see the warp, okay? So do you get the idea here, though, that we can't really put ourselves solidly into their world because we don't look like that. We don't have the same, we see things differently than they do because we're a higher dimensional being, right? When we look at this 2-dimensional universe, we see one line embedded with something above and below, but those words wouldn't even exist for them, right? Yeah.
So you said if they were translated into our world, they wouldn't be able to see it?
Right, okay, one way to get at that, we started just mentioning this, so how could we interact with them? Like if I were to put my hand through the board, what would they see?
The line.
All they would see is just the intersection of my hand with their universe, right? So if I stick my finger through, they're just going to see a little short line segment, and as I put my whole hand through, it's going to get thicker and thicker, and if I put my whole body through, it gets even thicker. But that doesn't mean a lot to them. Right? And you might say something like, well, here, just do this. Just stack up all those little pictures, and it'll make an image. Like, for example, if you took a bunch of coins of various diameters, you could stack something up that might look like a sphere, right? And you could say, well, that's fine. Just take each one of those little circles, and if you imagine stacking those on top of each other, what shape would you create? How come that doesn't work for them?
They don't understand the shapes.
Yeah. On top. What's that word top? There's no frame of reference in their universe, right? So we're limited, right? We're limited. We can never really understand what they see, but yeah.
So then, because of that, if we were able to transcend our own universe, I guess, would we even understand it if we got?
No. And I mean, this is, you can't.
We wouldn't even notice.
No.
So then how do we know we haven't?
Question?
We don't.
So, but don't they have vision of like forward this way and then back?
So they could say, let's just say, they live in a 2-dimensional universe. So they could, looking out here like this, from the perspective of Mrs. Scarlett, I could say, okay, Mr. Blue's gonna move to the left, right? If I tilt it this way, that's left and that's right.
But
yeah.
Aren't the only 2 dimensions? Like I don't feel like red and blue can see each other at all because they have the faces or what is like the dimension. So like why can they see to the side of them?
Well, because okay, that's not much of a stretch. Like what's Mrs. Red gonna see if Mr. Blue just walks down there?
A blue line changing position.
Exactly. She's gonna see a blue line segment that's shifting in her, linear field of vision, right? What's he doing now? What's she seeing?
Getting bigger.
Getting bigger, right? So just like we can't really see, backward and forward, we can interpret the size of somebody being far away as meaning they've gone that way, right? But we don't see in 3D. We just see 2-dimensional pictures. Yeah.
There's no thickness to those.
You're right.
So then how could they possibly see a thickness? Because like you're describing it as if there's one sort of line with like a color on it.
That's expanded.
Right.
I
But
don't
you're
feel like that though. I feel like they would see out the faces. The face of, I feel like they can only comprehend what is on either side of the face of whatever object they have because they have no width.
right.
So hence why I said yesterday that they should just see a still of this classroom as if it was two-dimensional.
Well, I mean, we're getting probably a little bit mired in a non-existent universe, but you can't forget that you're thinking about this from the perspective of you, right? That's not what, they don't, I mean, who knows what their two-dimensional eyes would see, but all they have access to is this, right? And so they're gonna see regardless of what it's gonna look like to a flat, who knows? But I mean, from our perspective, it would look like a white line with a little blue line segment that's getting bigger, now it's getting smaller, right? They can conceive of the fact that if Mr. Green, well, actually, how about orange? If Mr. Orange is bigger, if he walks in front of Mr. Blue, well, just like I don't think that Lily disappeared from existence, they would understand that they're smart. They would understand that there's a two-dimensional relationship in their positions, right? So we get the idea. I mean, we don't need to take this any further than that probably. But here's the thing about flatland. Flatland works just like our universe. If we put some object that has flat mass in their universe, what do you think is going to happen? Like if they were to, let's say, here's a source of flat mass. So it's going to be, it provides some flat gravity. All right? Oh, that's good actually. That would be great. So if they're playing flat ball in flatland and Mr. Red wants to throw the ball to Mr. Blue, but this is a gravitational center, right? It's a source of gravity. What does he have to do?
Throw it yellow. Throw it towards yellow.
Okay, good, because if he throws it in a straight line like this, what's going to happen? It's going to curve up towards the pull of gravity, right? So he has to compensate for that, just like we do, right? If I want to throw a ball to Nick, do I throw it straight at him? No, I lob it up in the air, right? Same thing they're going to do, okay? Right? And Mr. Blue, who happens to be a flat physics teacher, he's having the same bizarre conversation with his flat class about what's the cause of this. You know, what if he drops this black flat marble and it falls towards the gravitational center? And they're smart flatlanders. They can do flat physics. They can do all the analogous stuff that we do, right? They can calculate the accelerations of this object. They can figure out what the flat velocity is going to be when it's gone a certain distance. They're great at that stuff, just like you guys are. Yeah.
So because they don't have the concept of up or down, when they drop something and just go down, it goes like whoop, like off to the side somewhere.
Well, sure. I mean, for us, where does it fall for us? It falls in one specific direction towards
The
center of the earth, right? Okay, well, they don't have access to up or down, so it just goes sideways.
But don't
Right.
they have up or down? 'Cause
I mean,
have
I guess you could call it up or down.
front, and back. They just don't have this.
They can only have
Depends
two
on
of them at a
two
time,
dimensions.
let's just say that. They could label them different things. Okay, but when this crazy blue flat physics teacher says that, okay, there's more to this, what's really happening, this guy Flat Einstein discovered that what's really going on is there's a warping of their universe that they can't see, that this marble is falling into, right? When they drop it, they're just as astounded as you are. It's not something they can directly perceive, but we can. What do you think is going to happen if we turn their flat universe sideways and this is a source of flat mass? It's going to dip down. Yeah, exactly. So if we take the flat universe, and let's go to another page here.
I know this is going to be tough, but is there any way we can apply this kind of thinking to a one-dimensional world? Or is that way beyond our thinking?
It's a good question. I mean, we could, well, think about that over the weekend. You tell me. You think about it over the weekend and tell me how that's going to work.
Would a point lander only comprehend himself?
Yeah, point landers would be tough. Or line landers. Yeah,
Yeah.
that'd be tough. I don't know. That might be a pretty boring universe.
How can you have flat gravity without,
You just have forward.
like, would it be like area-based gravity?
Yeah,
Okay.
yeah, volume to us is area to them. Yeah. All right, so let's take a look at this. So if this is the profile, now you gotta bear with me on this. If this is the profile of flatland, right?
Oh, we're around.
Okay, there's flatland in the absence of any gravity. Here is Mr. Blue, okay, seen in profile, right? That's what we were talking about. He's just a line segment. And here's Mrs. Red. And here's this gravitational center, right? It sits in between them somewhere. They're gonna have to try to curve it around, right? Throw it to the side. Okay, you told me that's gonna warp the space. It does, right? So if we were to draw the flat universe with the gravitational warp in there, does this make sense that it might look something like that? Right?
Yes.
And so here's that.
So it's three-dimensional.
Okay, but right, to us, right? Because we have access to that extra dimension.
To them, does it just cease to exist?
To them, it wouldn't look any different. It looks like our universe looks three-dimensional when I drop this pen, right? You can't see the warp because you're embedded in the three-dimensional universe.
Is that why we can't really comprehend black holes? Because it's just such a big,
Well,
such
I've
a
got
big warping that we don't even know what's going on.
Hold that question.
Okay.
Because well, let me ask you a question. If this is what a source in flatland, a source of flat mass looks like, the bigger the mass, what do you suppose happens to the divot?
The bigger the drop.
Okay, the deeper, the more extreme the divot gets. What do you think might happen if you exceeded the flatland equivalent of the neutron degeneracy pressure and the universe could no longer prevent something from imploding on itself?
There's space.
What's going to happen to this? So a flat black hole, seen from our perspective, what do you think is going to happen to this pit?
It's gonna break deep.
Yeah, it's just going to go infinitely deep, exactly, right? And that's a real good model for the physics of a black hole, right? The point, we would call the event horizon the place beyond which even flat light could no longer escape because it closes off. Yeah. Question?
Isn't it? So in every universe diagram I've seen, it's always been like a U with like flat plane, like one plane kind of bending U, and then it has like the black hole that goes through the other side.
Say it again.
So could the universe be that line, and then in a U underneath it, and then that hole hit the other side and go through?
Okay, you're talking about like a wormhole.
Yeah.
Okay, we'll hold that thought. We'll get to it.
We'll get all the thoughts.
We'll get there. There's lots of thoughts that spring out of this. Okay, so then let's look at the effects of this, right? So from their perspective, they don't see this, right? Everything in their universe, including flat light, it's all relegated to live in the universe, just like ours is, right? Light is, by definition, light has no mass, right? We'll talk more about light later, but light is a little bizarre. It has no mass, and yet it has momentum. It has relativistic momentum. But light is not affected by gravity, right? If you shoot a laser, if I shoot a laser at that wall, it's different than if I throw a ball at the wall, and the ball is deflected by gravity, right? Why is the ball deflected by gravity? It has mass, right? Mass is affected by gravity. Light, on the other hand, doesn't do that. Light is always going to travel in a straight line.
If it doesn't have mass, it's pulled by a black hole.
Is light second dimensional?
No.
Is that volume?
But light travels in a straight line, but it happens to travel in a straight line through a warped universe, right? And as bizarre as all this stuff sounds, you might be asking the question, prove this. I mean, what you're telling me is pretty bizarre. Okay, here's some proof. Here's some proof. If you look at a star during an eclipse, so let's say here's our sun.
Like this summer.
Like this summer, exactly, yeah. What's interesting about this is, as early as, like within the last 100 years, this was considered to be weird. When Einstein first posited general relativity, and he suggested this is the way gravity works, people laughed at him. They thought he was a kook. Until this happened.
They realized he's right.
until, if this is our sun, that's a pretty good sun. If this is our sun, when it's blocked by the moon, so we're able to filter out all that intense light. See, kind of wacky stuff in there.
No, I could see her on
Yeah. See, yeah. So when this is covered up by the moon and we're able to see, block out all that light, and for example, a star that should be invisible because it's being blocked by the sun, we shouldn't be able to see it. Well, as the sun moves in the sky, as the Earth rotates and it moves closer to that star, what happens is the star that should be back there migrates and ends up being there.
Could you repeat that?
Yes.
Yeah.
The last.
Yeah. So if we're looking directly at the sun,
Can you put the moon in front of it so I can understand?
well, the moon is just going to block it, right?
The moon just, so the
Gets rid of excess light.
Right. So this would be this will happen. It's not just because of the eclipse this happens. It's because of the eclipse we can see it, but it happens every day.
Okay.
You just can't see it very well because the corona of the sun's so bright you can't see the star.
Okay, is the star the same as the sun, or are we, the stars are different?
We could just
No,
put
but
behind-
this is-
Could we just for this example? Could we just replace the sun with just a ball of mass?
Sure. Yeah, you could. The sun could just be a ball of mass, right?
But is this a different star we're talking about?
Yeah, it is. So there's some distant star that, now we know where all the stars are going to be at every second of every day because they don't move very fast, right? I mean, they're pretty much fixed, and they do drift a little bit as the galaxy evolves. But if this is just some star in our galaxy, the star charts tell us it's right there for sure at that time of day, absolutely, except for the fact that the sun happened to wander between us and the star, which warped space in such a way that there now is a straight line path between our eyes and that star where there didn't used to be.
Wait, can you
Right.
start? I'm getting stuck on where the sun is and the star is.
Okay, the star is behind the sun.
It's behind it. It's truly
Okay.
behind the sun, but it's truly not behind the sun also because behind the sun changed when the sun moved between us and the star. Well, because it's honestly it's choosing your words on this. You got to be careful because it's easy to oversimplify this, right? It's that you can only see light travels in a straight line only. It does not. It doesn't bend gravitationally. It bends because space is bent, but it doesn't bend through a space because of gravitational deflection. In other words, you could say that there's kind of two kinds of gravitational deflection. There's direct gravitational deflection, which is an artifact of just Newton's universal law of gravitation, right? And that means that any object with mass is going to be, its trajectory is going to be fundamentally affected by the fact that there is a force acting on it that's going to accelerate it, right? Light is not accelerated by mass. Light travels in a straight line, but if the space through which the light is traveling is warped, then is that really warped? I mean, it is the straightest path, but the path has just been changed, right? And you got to really just hold questions for just seconds. I got you. You really got to absorb this because this is a big thing. But when you get this, this is going to be cool. There's some breakthroughs that are going to come here. The bulbs are going to go on. So when we say that the apparent position of that star has changed, we are lying. The position of the star really did change relative to us. It really did, because what does it mean to say the position of a star relative to us? That just means the path of shortest distance, because that's what light always travels. The path of shortest distance was reconfigured by the warping of space, right?
Caused by.
Caused by
The sun.
the sun, the mass of the sun. The mass of the sun created a divot in the universe that caused that straight line path to be altered. If we were to look at this from a different perspective, yes?
Okay, so let's say the sun is a lot bigger, like the blue star, isn't that the big one, right?
Right.
Okay. Could you possibly see a star that's to the left of the sun on the right?
Well, yeah, you can.
Oh.
It doesn't, okay, but what happens with that, and I'll show you some pictures. This is all just called gravitational lensing, is what this is.
But, so does that mean,
Some pictures? Yeah, I will. But the pictures, unless you know what you're looking at, the pictures aren't gonna mean much.
So does that mean anything that is behind the sun we'll be able to see? Because the sun
No,
is
not
so
anything,
far?
because the sun isn't very massive. So the sun doesn't create much of a warp. It
But
really-
just a little bit, like.
A little bit, right. And so the impact isn't very dramatic. A star that would be there might end up being
Okay,
there.
so we're saying
Right.
if the star is close enough to the back of the sun, then
No, it's close enough to be outside of the sun. Or the-
Well, yeah. So seen from a different perspective now, if instead of looking at the sun, if now we're here and the star is there, let's say, right? Here's what happens. Okay, and so here's Earth. This is not drawn to scale. Here's the star,
oh, pretty cool.
right? So here's one way to look at it. You could say that the line that the light follows is doing this, right? But you gotta be careful with that, because doesn't that seem to imply that if I were to take a spaceship coated in
Equilibrium.
Codium.
coulium,
Code.
which is impervious to heat, it's complete insulator, and you travel, doesn't it make sense that you could travel, based on this picture, what if I just went in that direction, right through the sun, right?
Then you would
Wouldn't I get there quicker?
No, you travel through
Yeah.
warp space.
Yeah, exactly, so I wouldn't. If I traveled through the sun, what would happen is the warping of space would cause me to miss it to the left.
So does that mean a wrinkle in time has some validity?
Yes, it does. I mean, it's pretty basic. I mean, it's not great physics, but yes, there is. I mean, that is a possibility, and that's what a wormhole does. But you see what I'm saying, though? Traveling, there is no faster way to get to this star than following a light beam, because that is the shortest path through a warp space, right? You get the idea?
So, I'm gonna pitch the fact that light is second dimensional to you.
Well,
It has
you
no
can
volume.
do that, but I'm not going to buy it. Light's hard to describe. I mean, you got to kind of get used to the idea.
Is it trans?
And this was a little bit of a crushing blow to me when I first realized this, because I went into physics to know exactly the way things work, you know. But unfortunately, physics doesn't do that. Physics gives you models that help you make predictions. You can't. People oftentimes ask me things like, "What does an atom look like?" Well, an atom looks like nothing because it's smaller than a wavelength of light. An atom doesn't have, you know, what does a string look? You can't. You can't tell what it looks like. You can make representations of an atom that allow you to conceptualize what it might be like, but it's not, because you don't live in a place on a scale where quantum mechanics is meaningful,
Wait, so light's
right? I mean, it's
No, a wavelength.
a wavelength of light is bigger, much bigger than an
So
atom.
how big is a photon then?
How can you cut?
doing that?
So, well, I mean, because a wavelength of light is not just a little bigger; it's a lot bigger than that. And so,
A wavelength.
Wavelength is
of
two-dimensional.
a what?
Wavelength is two-dimensional.
It's well, I mean.
Light
You can represent it in a way that's got two-dimensional components, but technically, the electric field and the magnetic field in an electromagnetic wave are always at right angles, and they're perpendicular to the direction of propagation. So, I mean, I don't know, the two-dimensional thing, it's tough to do. It's tough to do because light really does. I mean, it really does fill volume. It really does. I mean, but once again, it's just difficult to try to conceptualize in terms of regular stuff. Like, you can't say light is like a bunch of ping pong balls thrown against a wall.
But it fills things in a straight line.
It does, yeah.
Nothing else fills things in a straight line.
But light also moves in waves.
Right. I mean, the
You don't need
Which
two
are not
waves to
straight
make a
lines.
wave.
the average position of the photons is a straight line. Yeah, but that's about all you can say. Because the photons, by the Heisenberg uncertainty principle, and this is bizarre, even with just a hydrogen atom, if you knew exactly what the velocity of the hydrogen atom was, or its energy, same thing, it could be any place in the universe, and it literally could. And so it's so weird when you start getting into quantum mechanics. Stuff happens, like this is quantum mechanics. If I stood here, and there's a reasonable high percentage chance that in a second I'll be out here with no time elapse, right? right? I mean, that doesn't happen. It doesn't happen on our scale. It just never does.
So this is going back on. Oh. So you can have a black hole that's like this, and like this, and like this, and like this, right?
Whoa.
A what now?
A black hole that goes like
The angles.
that.
In Flatland, you mean?
No, in our land.
Like, how, like,
In Earth.
which plane is a black hole on, and can there be many?
A black hole is not in any plane. A black hole
Is nothing.
A black hole is, I mean, because this is just a model, right? Our universe isn't like this, it's not flat, right? So a black hole, I mean, you can't visualize it.
Three-dimensional?
I mean,
Is
to
it
us it is,
four-dimensional?
but yeah, it has to be because it warps space. And really, honestly, I use the word 4 dimensions, I call it 4-dimensional to simplify things, but a black hole truly isn't 4-dimensional. It's more, it would be, to a physicist, it would probably be better to say that it's 6-dimensional, because for each of the 3 dimensions, you're going to introduce a new degree of freedom. So there's going to be a tidal effect and a compressional effect along each of the 6 dimensions, right?
So
So
should we just
each
do
of them
3
gets
for
split into 2 degrees of freedom. But it's, I mean, once again, it's when I say stuff like that, it's going to make you try to think about it in terms of what that looks like, and it doesn't look like anything. You can't know. Yeah.
So back to this model.
Yeah.
A star emits light in all directions, right?
Right.
So would there be a time when, if it was in the perfect position behind the sun or some other mass, that it would be both
Bow to both sides. of the
both
sun.
sides, so you could see it on both sides of the mass? I understand.
Well,
Like
okay.
neither one
Yeah.
is the shortest distance, they're
You see
both
half
short.
of the star on one side.
Okay, right, so what you can't do is this. You can't do,
It's
Oh,
Coulomb.
I'm just getting rid of Coulomb.
Coulomb.
Oh,
okay, you can't do this. This doesn't work if you say that light's gonna go, I'm gonna have a star there and a star there. And this one's gonna go like that, and this one's.
Wait,
no,
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 here,
that's not
here.
what I'm saying.
Okay.
You're saying
They're
one
saying
star.
put one right in the middle of those
One
two
of those.
stars, and it goes on both sides.
Oh, yeah, that's fine. I'll show
So
you
you
a
can
picture.
see the star twice.
Yeah, here's,
That's what you're saying.
all I'd have to do, yes, ma'am.
Fish with big eyes. No, there are fish like that. There are fish like that. Navy swordfish just have huge giant eyeballs and they have a body and they just kind of fall.
There you go, gravitational lensing ring. Watch this.
Mr. Oya?
Yep, question. Go ahead.
So do you actually die when you go into black holes?
Oh, yeah.
Your
No, you die long before you.
But your information would be saved.
Well, it very well might.
It's like a black hole, like a hard drive, like a.
That's a better question than you think, because it's one way to think about the universe as evolving is that it's actually computing itself, and you can completely quantify entropy as the universe acting as a computer.
So it would
So-
be like where they put like the thumb drive.
There you go. Yeah. There's an example. There's a lensing ring. So what caused this? Yeah, this was caused by something between us and a star, and for a black hole presumably. It's got to be something with a really powerful gravitational center. And when you look by that, space has been warped in such a way that it looks like a ring, right? It's coming from right directly behind the black hole, and so the light is all being warped around it. And that's the effect. That's a real picture of our universe. So this does happen, right? Okay, so then if we go back to Flatland, right? There are some effects here that you can start to begin to understand. Like, these guys cannot see this warp, right? If they were to walk from here to here, they would walk along this path, and the whole time it would seem completely flat to them, right? The warping is only visible to us, right? Does that make sense? Okay. And so if they were to, like if they were to try to put something in orbit around this flat planet or whatever this is, all they'd have to do is give it some tangential velocity. So from our perspective, it would be making a ring, right? Does that make sense?
What would be making a ring?
Well, we would see it It's kind of rotating around the neck of this
Oh.
divot, right? All they would see, they wouldn't see that. All they would see is this. Right, you get the idea, right?
Yes.
Okay. I'll give you another piece of evidence in case you're still skeptical. Okay, it doesn't take very much physics to try to understand, like if we're gonna launch a rocket to Mars, the physics is not that complicated. The kinds actually I went to school with a guy in undergrad who used to fly down to JPL on weekends. They'd fly him down because he had, as one of his junior year project, he wrote an improvement to the Monte Carlo approximation method they used to track satellites. So they had to go upload this thing. His name was Hal. We called him Hal 9000. He was a pretty smart guy. But he did his undergrad. I mean, you know what I mean? He was really smart and he knew a heck of a lot of math, but still, it's not like you had to have 14 graduate degrees to understand how to program a computer to track these satellites. It's really just basic physics. And so we can, I'm going to show you some laws here in the next few days, Kepler's laws that are very helpful. I mean, using just these really simple classical physics laws, we can make accurate predictions about where Saturn is going to be in exactly 1,141 years and 10 hours and 3 seconds. I mean, we can tell you exactly where its center of mass is going to be. And we're going to be very, very close to being right. We can do that for all the planets. And we've been able to do this for a long time, hundreds of years. But there was a problem. Mercury didn't work. There was a perihelial shift in Mercury, and it would always end up being not in the exact place it should be based on its distance from the sun and its speed. It was wrong. All the other planets were exactly right, but Mercury was wrong. And nobody could explain this. People came up with bizarre, I mean, this is going to sound crazy now when we talk about this, but people came up with explanations like there's this stuff called the luminiferous ether that permeates space, and it congregates around the sun because of its mass, and it's like it's moving through a gas then, and it slows it down. And so there were all these bizarre. We know that's not right. But at the time, it was the best we could do. There was no way to explain this. Okay, what was going on? What was going on there?
The light.
It wasn't the light. What was going on? When we measure, if we look in profile here at what we measure to be the distance between Mercury and the sun, right? What are we going to measure? If we were to walk from there to there, what we're really doing is we're really walking along that warped path, right? Look straight to us though, right? So this is the distance. When we measure the distance from the center of mass of Mercury to the center of mass of the sun, we're measuring that distance. Is that distance, you tell me, is that distance shorter or longer than
It's longer.
the distance that we actually believe we're walking?
Longer.
It's longer, right? It's like if you were to take a basketball and you were to take say you had a rubber ring and you were going to take a flat rubber ring and stretch it down over the top of the basketball, right? Gravity does that to our space. We call it a spherical warping. So this is the flatland equivalent of what it would do. If this is the basketball, and here's the rubber ring that we're going to pull down over the top of that. What's it going to look like? Well, there's going to be the border around, right? That makes sense? And then if there's a spot in the exact center, that's going to go on the North Pole. But these lines that seem to be flat are actually like lines of longitude on our planet, right? This is what gravity does. The presence of mass in the universe spherically warps space. So what does spherically warped space mean? That in flatland, right? If flatland is the surface of there's a two-dimensional surface on the spherical ball, right? When you pull this down, you end up with the Euclidean geometry no longer working, right? We're used to, in a flat space, And we talk about the universe, we ask the question, is the universe flat? And although Earth is not flat, for sure, the universe is very nearly flat. When we say that, though, we just mean that if we draw a circle, if we draw a circle, and we measure its circumference, and we measure its radius, it means that this is true. Right? Okay, that is true for us in our universe. But it's in some places. But it's not true near the sun. Right? Near the sun, it doesn't work. Near the sun, this is the radius, and this is the circumference. In this case, the circumference is less than 2 pi r. Right? It doesn't fit its own flat circumference, the radius. Right? And so we're using this distance, or this distance, instead of this one when we use classical physics, or geometry. Right? And so we were calculating where Mercury should be based on Euclidean geometry, and it's not the way it works. Einstein showed us that the universe gets warped in such a way that the path is different than what it would be in a flat space because of the warping of space. And so when you do the math, when you apply Einstein's equations, they exactly predicted where Mercury should go. And all of a sudden he was no longer a kook.
So how did that not work for the other planets as much?
Because they're far enough away from the warp that
Where
space
it's
is.
almost the same.
They're far enough away that space is essentially flat there, right?
But it's not quite flat. It's nowhere's quite flat, right?
Well, on average, it's flat there. Yeah, it's.
But it's never like 100% flat, right?
I mean, that's tough to answer because there are some things that can actually cause the opposite of a spherical warping, which is a hyperbolic warping.
Oh, yeah.
So, on average, it
Of a sphere.
it's a saddle where it's going to go up like this and down like that. So it's a saddle shape. That'd be the flatland equivalent of a hyperbolic warping of space.
Are we just working on the UTA?
What's that?
Are we just working on the UTA?
Yeah.
Is there go to your library?
Yeah, that's fine. Yeah.
Thank you.
That's pretty crazy stuff, isn't it?
Yes.